So you've seen in class already the qualitative aspects of the force between different electric charge. Today we need to quantify that force using the Coulomb's law. And this is following chapter 21 in Young and Friedman. If you were to put the law into words, you could simply state it as the magnitude, which is a scalar, of the electrostatic force, and I'll use an abbreviation ES throughout. That force itself is a vector quantity. The magnitude of this force depends on two things: the distance, r, between two point charges, and we want to be clear that r is always a positive quantity. Distance must be positive. And that force magnitude depends on the product of the charge magnitudes. We'll call each charge Q1 and Q2. And it's very important here because we are dealing with the magnitude of a vector, which must be a positive quantity. You must be careful to use the absolute value of the charges, noting that Q is a signed scalar with both a magnitude and a plus or minus sign. So you'll see throughout the course various situations where you need to maintain the sign of Q in your formula because it is a vector formula. In this case, we're dealing with a law that tells us only the magnitude of the force between these point charges, and you'll have to use your rules that we learned in class about opposite charges attracting one another and same sign charges repelling each other. You have to use those rules to determine the force direction. So an example here, we have point charges Q1 and Q2. It's important to note that only point charges are treatable using Coulomb's law. So we could say that Coulomb's law only applies to zero-dimensional or point-like objects. We'll have situations where you may approximate a macroscopic object as a point charge, assuming that the distance between the two charges is much greater than the size of the object. So we'll take an example where both charges Q1 and Q2 are positive. So you should be able to tell me at this point that their force on one another should be a repelling force. We have the force vector 1 on 2, the vector sign, and force vector 2 on 1, pushing charge 1 away from charge 2. We must label the positive distance, r, between the charges in our diagram. With this picture in mind, now, we can construct the scalar equation that represents Coulomb's law. The scalar, because we're simply talking about the magnitude of the force vector. This is equal to lowercase k, which we call Coulomb's constant, magnitude charge 1, magnitude charge 2, all divided by the square of the distance between those 2 point charges. That Coulomb's constant has a value of 8.988 times 10 to the 9 Newton meter squared per Coulomb squared. You can see it's a proportionality constant that must create a force on the left-hand side, so we need newtons in the numerator. It must cancel out the 2 coulombs in the numerator, so we have per Coulomb squared, and it must cancel out the 2 factors of a meter in the denominator, so you have meter squared on top. Again, we call this Coulomb's constant. This is a fundamental constant that's provided on your formula sheets. During the exam, you don't need to memorize its value. It is intimately related to the quantity epsilon naught, epsilon sub 0. 1 over 4 pi k is epsilon naught, and k is 1 over 4 pi epsilon naught. They have an inverse relationship. Its value is 8.854 times 10 to the minus 12, and you simply need to invert the units here, so Coulomb squared per Newton meter squared. This is called the permittivity of free space. We'll talk about this more in class, but you should think of it as a quantity that defines how much the universe is allowing other charges to feel one another. Of course, we have to determine the direction of the forces here. Which is given by the rules of attraction which we see in the case of opposite charges and repulsion in the case of same sign charges. You can see in the image, these are 2 objects placing a force on one another. So we should expect that those forces are a third law pair. Newton's third law tells us that the vector force 1 on 2 is the negative vector force 2 on 1. The objects are placing equal and opposite forces on one another. Now be very careful that you do not apply this to the scalar magnitude of the forces. I don't want to see you writing this. Right? This is bad. Scalar magnitudes of forces are all positive. You should get used to the idea that the scalar magnitude of the force 1 on 2 is equal to the scalar magnitude of the force 2 on 1, even though the vector forces are opposite one another. So let's try a numerical example here. What is the force magnitude between two positive 1 Coulomb charges placed 100 meters apart? The Coulomb, as you will learn, is an extremely large amount of charge. And if you're working force problems with any significant fraction of a Coulomb, you're going to find some hefty forces involved. For this particular estimation, I'll simply use 9, 10 to the 9 in place of Coulomb's constant. So we take the scalar magnitude formula here. I'll use 9 billion Newton meters squared per Coulomb squared. The magnitude of each charge is 1 Coulomb. They were positive. And we're placing them 100 meters apart. You can see that this force works to be 9, 10 to the 9 divided by 10 to the 4. So we have 9, 10 to the 5 newtons, or 900 kilonewtons of force. These are both positive charges. In this example, they're being forced apart from one another. If you were to attempt to place this large amount of charge, a full Coulomb, on two small cars, whose individual weights perhaps 10,000 newtons, if we estimate a small car as 1,000 kilograms or a metric ton, estimate G as 10 meters per second squared, we get something on the order of 10,000 newtons. So if you think literally here, these two small cars separated by 100 meters. Here's a 1 Coulomb car and another 1 Coulomb car. They're individually pulled down by a weight attraction to the center of the Earth, which is 10,000 newtons. But they are being pushed apart by this massive 900,000 Newton force due to the presence of this 1 Coulomb charge. As a final example, I will look at the case where 2 point charges, call them capital Q's now, Q1 and Q2, are separated by a distance capital R. If we triple both charge magnitudes, and triple the distance between them, how does the Coulomb force change? Well, we could write out what was the original force, or what was the old force. It's K magnitude Q1, magnitude Q2, over capital R squared. The new force, after the changes take effect, has a magnitude K times 3Q1, absolute value 3Q2, divided by now a distance which is 3 times R. Be careful to square the new distance in full. So if we look at the change as a ratio, say the new force magnitude over the old force magnitude, you have 9K Q1, Q2 divide by 9R squared for our new force, and our old force was simply K magnitude Q1, Q2 over 1R squared. K, Q1, Q2 magnitudes and R squared all cancel out. On the top we have 9 over 9. At the bottom we're just left with a 1. So we're left with this conclusion here that the force magnitude remains the same.